Hey guys, I am going to try to walk you through what I was doing with the Cater's pendulum. It's a really simple experiment, but I haven't thought about exactly what I want to say, so this is going to all come out in a long and discombobulated ramble. There's a little bit of infrastructure here. There's some aluminum posts that I bolted to a table, and they're resting on the floor, and they are held together with two cross pieces, which is just meant to provide us with a rigid frame here. What we would like to have is a situation where the pendulum is suspended from some superstructure that is immobile, right? That has infinite mass and doesn't move, so that we're just studying the motion of the one, there we go, isolated component and not some complicated system. That's not realistic, but building this apparatus this way gives us enough rigidity for this to work. The actual pendulum is this brass guy. It is a brass bar that's mostly symmetric, except for those two holes, which are not placed in the same position. And at the moment, it has an adjustable slider on it. All right, so we'll remove that. Lightweight. Oh, what is that? I think it's actually nylon, but it's a lightweight chunk of plastic that just can be moved up and down the pendulum. All right, so the pendulum is suspended from the quote-unquote knife edge, which is just some jargon that has persisted for a very long time when talking about this kind of stuff. You can see there, it's cut from a piece of tool steel. So it's very hard, and can't really get a better view of it than that, I suppose. It has a right angle that the hole for the pendulum can rest on, and that provides a support. So it looks like this. Sorry, the computer made a bunch of weird sounds because I was resting this microphone on the keys. But it's a little sharp edge, and then the top part of the circle cutout will rest on that. So there's two ways to run this experiment. Actually, before I go into that, let me just talk about the last piece of equipment, which is a photo gate. It's the same kind of equipment you used in your introductory physics labs. This gizmo has a beam of IR light, and when it's interrupted and then restored, a counter over here will just make a little tick in time. So you can set this thing up to run a couple different ways. It helps if you plug it in. Okay, you can set this counter up a couple different ways. There are two photo gates that came with it. Who cares? It's not fundamental to the physics. It is a kind of precision instrument, only insofar as it has pretty good accuracy. It uses a quartz crystal oscillator. That's the same thing that shows up in a $5 wristwatch. So does that really count as precision? No, but we're talking about measuring G to 1 part in 10 to the 4 or something like that kind of error. So we have to make sure that we are using an instrument that allows us to do that. I just turned it off again like an idiot. Okay. I will change it to the right mode. Now, if I place the pendulum on the knife edge and let it interrupt and then open back up the beam in a periodic manner, this thing will count up the number of cycles that have passed. Then after X number of cycles have occurred, I can get it to spit out the period of the last 20 cycles. So what I do to run this thing, we'll do the quick measurement method first, is I place the pendulum on the knife edge from one of the two holes, and I choose a side to face out. This is a real physical device. It's not machined perfectly. It's a decent machine job. So it has some mechanical tolerance issues, right? So if I suspend it facing this way versus this way, there may be some roughness in that mount that is more of a systematic issue when mounted one way as opposed to the other. So moving this thing around and mounting it a couple different times is actually not the worst thing to do, which is one of the reasons why the preferred method is suggested, because the idea being we're not relying on a small number of measurements with systematic errors. We're relying on a large number of measurements where we might actually be able to reclassify that as a random error, right? how was the thing mounted? All right, so I'm going to mount this thing. Then I'm going to stare at the way it's mounted using a magnifying lens. So on that brass on steel contact, there's enough friction that if I just clop the thing on there, it might not actually rest right at the top of the hole. It could be that the knife edge is actually kind of sticking and preventing the thing from slipping to its ideal position. I'll sketch that quickly. That's all I mean, right? Like it could be shifted off to one side. So you fidget with it a little bit to make sure that the thing's mounted properly. And we stare at it from the, I don't know what to call that, direction parallel to the plane of motion. We stare at it to make sure that it's actually lined up flat. It's oscillating with just about almost the right amplitude to trigger this thing properly. There's the sine theta is equal to theta approximation that we invoke for this pendulum. It's one of the things we could correct for to get a better result, but we're not doing it this first go around at least. So we want to have a small amplitude of oscillation. It needs to be big enough that the second hole opens and then closes that IR beam. And that's actually the most fussy part of this experiment. If you don't get it so that it is lined up in the way that the counter interprets these pulses, you get kind of nonsense, or not nonsense. You get data that don't represent the actual periodic motion of the object, right? What we're trying to do is to measure its period. We'll do it 20 times in a row. And if we don't have that thing lined up quite right, we'll get like a double counting or something, or even just a number that's hard to connect intuitively to the period of the oscillation. So this thing has run through 75 cycles. I'm going to take a look at them, and it's going to tell me something that annoys me, which is that the period for these things is a little bit wacky, I think. 1.939 seconds, 2.014 seconds. That, right? So it's returning a result of 2 seconds. And that's wrong. I know that that's wrong because I can sit here and watch this thing. I did it. I perturbed it and said, all right, I'm going to wait for 50 cycles. And I timed it and it took about 50 seconds. The period of this thing is really close to 1 second, regardless of which way it's suspended. So if it's returning only a 2-second period, it means I'm not actually triggering the photosensor quite the way I want to. So I'm going to give this guy a bigger thumb. And I just kind of played with it a little bit to find a compromise where I wasn't putting too much motion into the system. It's still only oscillating about a centimeter and a half, which is getting to the point where I actually am sort of at the edge of that sine theta is equal to theta approximation. But it should be triggering the counter properly now. So let's take a look at that. .005 seconds. I don't have it lined up quite right. 1.619. That's what I mean about getting nonsense results. 1.0 seconds. All right. So after that first initial wiggling, did I get it all working at 1.00 seconds? Yeah. So actually, I think this is probably working well. 0.9915 seconds. So let's take a look at the motion really quickly. So what I do is I set the pendulum up. I make sure it's moving the way I want it to. There are a couple other ways I can fiddle with it to make sure that the thing is lined up exactly right on the knife edge. And then I poke it and I wait for any extra motion I put into the system that isn't that simple back and forth mode. If it's got a wobble in it because of the way I pushed it, that actually damps out faster than the ideal motion, semi-ideal motion. So I just wait for a couple minutes, and the amplitude of that oscillation hasn't usually decayed that much. So I'll give it 2 or 3 minutes and let the thing run until it's in a definite long-term steady state solution, right? Okay, then I'll collect 20 or 40 data points to record the period. That is one measurement, right? All right, now I need to measure the pendulum when it's suspended from the opposite hole. But before I do that, I'm actually going to flip it so that I can record on the same cutout hole, but with the thing just flipped 180 degrees. So I'll just do this. And I'll go through that whole rigmarole again to line it up, right? So when I've done that, that is a measurement on this suspension point with both faces. Okay, having done that, gotten 20 or 40 data or 60 data points in order to give me better statistics, I will then flip the thing. And suspended from this second position. Whoa, it's way too much motion. Goodness sake. Suspended from the second position, I will record another 2 data points, flipping it 180 degrees. All right, so that's how I get a measurement of time T1 and T2. If I remember correctly, T1 is recorded when the hole close to the end is used as a suspension point, and T2 is recorded when you're using the hole 2/3 of the way. It's not quite 2/3, but 2/3-ish of the way along the bar as a suspension point. So that is the quick method, quote unquote. And it takes a little while to do. The preferred method is more of a pain in the butt. We need that plastic slidey thing. Okay, there is a pattern of little pinprick holes carved into this brass thing. They don't go all the way through, but they allow you to semi-repeatably align the plastic slider on the brass rod. They're spaced out by 1 centimeter increments. We measure 0 from that first one down here. So now what I will do is I will mount the pendulum. I'll record T1 here with the slider in the position 0 centimeters. Then I will flip the pendulum. I don't move the weight yet. I record T2 for this second position. I don't bother doing that 180 degree flip here thing because I'm not as concerned about screwing up my calculation, my result, by putting the thing on the knife edge wrong one time. I'm making more measurements, taking the thing off, putting it back on many, many times. So by doing that, I kind of reduce the risk of one bad job of suspending the pendulum, screwing up the entire data set. All right, so that would be data for T1 and T2. I'd get 20 or 40 points. That would be the data I need. Let me line that up. There we go. I get the data that I need for T1 and T2 for the slider in 0 centimeters position. Now I move it. That's the 1 centimeter position. I made up a rule. I invented my own where I said, okay, I'm going to make sure that when I look at this a certain way, if I see a certain fraction of the hole, I will call that slider lined up with that hole. So now it's in the 1 centimeter position. I suspend it from both holes, record T1, T2, and then I move the slider again. Slider is now in the position 2 centimeters, and I record T2, T1 for the slider in the 2 centimeter position. And I just did that the entire length of the brass bar, not the entire. I skipped some of these holes down at the end because they're not really relevant to the next step in the analysis. And also, it gets really hard to put the thing where you want when you're starting to get close to this suspension point, right? So the slider doesn't fit very tidily in with the what's it called? The photo gate. You've got to fiddle with that a little bit, but that's why there's no point at like 11 centimeters or something like that. I can't remember. All right, so there's a weakness to this, right? I recorded my data sequentially. I did 0, 1, 2, 3, 4, 5, 6, 7, 8, right? I should have done them randomly, and I didn't out of a kind of intellectual laziness. So why is this a problem? What if there's a long-term drift occurring in the environment where we're performing this experiment? What if the room was changing temperature? The building cycles on a regular schedule. I can show you the data. I record it in my own lab. So what if it were consistently getting colder over the course of this experiment? Then the distance between the two holes is actually going to have changed a little bit during the course of the experiment. Is that significant? Well, if we want, we can analyze that and make an estimate about how much of an error that would introduce. It would probably also result in a change in the airflow in the room, right? If the HVAC system were cycling on and off. I think it does that on like a 40-minute, 45-minute time scale. I can't remember. I can just post you an image of the daily variations in humidity and temperature, and you can easily see where the HVAC system's cycling on. All right, so recording data like this sequentially is a bad idea. I should have done it in a random order so that that effect that could be perturbing our system wouldn't be what dominates our data set. If it's distributed randomly across the data, we might get a result that seems weird, but we're not going to observe some trend and say, oh, that trend is determined by the thing we're doing, when really the trend is determined by the HVAC system design, right? So, bad choice. But it was midnight and I was lazy. All right, I think that's everything you need to know for running this experiment. If there's anything ambiguous, take a look first at that teletomic manual. It's pretty useful. And then that PDF with some analysis of Cater's pendulum would be a good place to start. I have some other papers on this topic if you want, but they were mostly not meant to be as pedagogically useful. So I can absolutely hand them off to you if you like I tend to think that throwing more reading at a problem is usually a good way to overcome it. So we can absolutely do that if you're having any difficulties. I think that's everything you need to know. So shoot me a line if you have any problems with this as it stands at the moment. All right. Talk to you guys soon.